soon. So anybody come in late, I'm not going to admit them anymore so that it does not interrupt my lecture. Okay, so we're going to continue with chapter 6 on line code, yeah. Okay, can you see my screen?
Yes.
Yes, Miss.
Yes.
So last lecture, we actually stopped here where we compare the bandwidth of a few types of line code. All right, and I want to make one correction over here. Okay, is that at this stage now we haven't even done pulse shaping. So please cancel this line. All right, we haven't done pulse shaping yet. So what we can see from here is the bipolar line codes actually give us the smallest bandwidth, which is similar to the bit rate. All right, whereas the polar, all right, the polar, which is this line over here, all right, we give us a bandwidth which is close to 2 times the bit rate. Okay, so this is a comparison between different line codes on bandwidth requirement. Okay, so I've added one more slide, so you may want to take this now later on. This is on the comparison of the power, all right, of the power that we actually transmit using different line coding methods. So let's look at the first. We just want to compare two, that's all right, and the rest you can actually do it on your own, right? The concept is similar. So now I want to compare two types of line code. All right, one is the on-off keying, which is OOK, and the other one is the polar line code. All right. And then under each type of line code, we can use the non-return to zero format, or we use the return to zero format. All right, non-return to zero. If you use non-return to zero OOK, that means you're going to use a full width line code. All right, and then return to zero, meaning we're going to use half width. So what it means is, okay, let me write down. FW stands for full width. All right, and HW stands for half width. Right, and RZ, you know what it means, non-return to zero and return to zero. And then for polar as well, we are going to compare the bandwidth requirement for polar using the non-return to zero version and also the return to zero version. Okay, we're going to transmit the same binary bit stream. So we're going to transmit 1011. All right. So 1011, if you were to transmit using the on-off keying with the non-return to zero pulse, yeah. So what that means is when we transmit one, we transmit a pulse, non-return to zero. So it lasts for the entire bit duration. Then it go back to zero because we transmit the next bit, which is a zero. So it goes down to zero. All right, and then the next time I need to transmit is a one, so it's going to go to one, and then the next bit is one, so it continue to stay at one. All right, and let's say this is zero, this is your zero. Let's say we use a pulse with the amplitude A. I'm going to call it A here. Yeah, so this is for on-off keying, non-return to zero or full wave. All right, on-off meaning I transmit one with the pulse that's on, and with the zero, I off the pulse. Okay, and then the return to zero half wave means when I transmit a one, all right, I send a pulse that lasts for the half of the duration of the bit. All right, and then goes down to zero. Yeah, and then to transmit zero, we don't send anything, so we stay at zero. Okay, and then the next one, I'm not transmitting is a one, so the pulse go up to let's say amplitude A again. then for half of the bit duration, and then it goes back to 0. All right, and then the next one, it go up again for half of the bit duration, and then goes down to 0. Okay, so this is A, this is 0, and this is A. Okay, on, off. Again, on the pulse with the amplitude A, off the pulse, so nothing. Amplitude is 0. Okay, and then for polar non-return to 0, polar non-return 0, so to transmit a 1, we transmit a pulse with the amplitude A, non-return to 0, therefore it lasts for the entire bit duration. And when we transmit 0, is polar, so 0 is transmit with the pulse amplitude minus A. All right, so it lasts for the entire bit duration, then it goes back to 1. Because I'm going to transmit a 1, so it goes back to amplitude A, and then the next bit is still 1, so it stay at amplitude A. So this is 0, this is A, and this is minus A. All right, in polar, a 1 is transmitted with the pulse of amplitude A, whereas a 0 is transmitted with the pulse with the negative pulse. Again, the amplitude is A as well. And then for polar return to 0, all right, we transmit a pulse that lasts for half of the bit duration, and then goes to 0. And to transmit a 0, we send a negative pulse, lasts for half of the bit duration, and then goes back to 0. Then transmit a 1, we send a pulse that is positive, lasts for half bit duration. Then the next one is going to transmit in the same manner. All right, this is called half wave. If quarter wave, then it's 1/4 of the entire bit duration. All right, as the name suggests. Then let me mark the bit duration first. Okay, this is your bit duration, and I'm call it TB. Okay, duration of a bit. And then for return to 0, the TB is this. Half of the time is on, the other half of the time is off. All right, for this one, this is my TB. And then for this one, this is my TB. Okay. So looking at the binary stream or the electrical waveform that we use to transmit the binary stream, what is the power of the binary 1 pulse? To transmit a binary 1, what is the power used? Given the amplitude is A. Okay, so because the amplitude is the same and lasts for the entire bit duration, therefore the power used to transmit a binary 1 pulse is A square, right? Yeah, you just treat it like a DC that lasts for the entire bit duration. So the power is A square. All right. And then the power when we transmit a 0 pulse, nothing, isn't it? Because we transmit nothing. So therefore, 0 power is used when we transmit binary 0. Okay, tell your friend I'm not going to admit them until I finish this one. Okay, I'm not going to redraw the entire slide anymore. Okay, average power. What is the average power used then? Okay, average power. Again, we compute average power based on the assumption that the probability of 1 is the same as the probability of transmitting a 0, which is half. Okay, so that means we're going to transmit equal number of 1s and equal numbers of 0s. Yeah, and therefore our average power now is we add these two up and we divide by 2, isn't it? All right, so that gives us A square over 2. All right, which is the average power used to transmit a non-return to 0 on-off keying pulses. Yeah. Then what is the average energy per bit? Okay, you're going to see in your practical session the EB a lot. EB stands for average energy per bit. All right, so how much energy is used to transmit one bit then? Yeah, so this one can be found by taking the power multiply with your bit duration. Okay, and this is a square over 2 times TB. All right. Then let's move on to return to 0. All right, if we transmit the on-off keying pulses with the return to 0 format, then what is the power when we actually transmit a binary 1 pulse? What is the power? Now, because the pulse only lasts for half of the bit duration, now the power need to divide by 2 lah, right? A square over 2, isn't it? And then the power used to transmit binary 0 is 0 because we never send any pulse. Okay, so the average power again, add these two up, divide by 2. So that will give you the average power of a square over 4. All right, a square over 4. And what is the average energy per bit? So that is a square over 4 times TB. Yeah. So that is for on-off keying. All right. When we transmit on-off using on-off keying line codes with the non-return to 0 format, meaning we use a full wave pulse, then the average power is a square over 2. And what is A? A is the amplitude of the pulse. All right. And with return to 0 format, which is half wave in this case, then the average power is a square over 4. So you can see that even though we transmit with the same amplitude, all right, the power that transmitted is actually only half. Right, RZ, the power of the signal that we transmit is only half of the power of the NRZ. Okay, so any questions here before I move on to Paula? No? Okay, no, then let's look at Paula. In Paula signaling, all right, if we use non-return to 0 pulses, so again, the power that we actually transmit when we transmit a binary 1 pulse with the amplitude A, basically is A square, right? Because this lasts for the entire bit duration. And the power when we actually use to transmit binary 0, because we transmit binary 0 with the amplitude of minus A, so power is your voltage square, right? Or amplitude square in this case. So this is A square. All right. Then what's the average power? Average power is just A square. All right. So energy per bit now is A square times TB. Okay. All right. Then let's talk about return to 0 polar code then. So for a return to 0 polar code, now because the square pulse only lasts for half of the bit duration, therefore the power used is A square over 2. All right. When we transmit a binary 1. When we transmit a binary 0, again, okay, let me mark here. I forgot to mark here. This is 0, this is A, and then this is minus A. All right, when we transmit a binary 0, again, we use A square over 2 as well, our power. So the average power is, what's our average power? A square over 2, right? Yeah, so and the average energy per bit will be A square over 2 times TB. Okay, so let's compare these 4 methods. All right, if we transmit all of them with the same amplitude, all right, which one actually generate more power. The
Polar non-return 0.
polar non-return to zero, isn't it? Yeah. So let's do a short conclusion here. With the same amplitude, all right, basically the polar coding in general, all right, polar code power is actually 2 times the OOK power, isn't it? All right, it's 2 times the OOK code power, isn't it? It actually produces 2 times the power. So what does 2 times the power mean? Okay, so that means your polar code is going to give you better SNR, right? Yeah, better signal to noise ratio. All right, given same, these two type of coding actually is sent over the same channel. All right, that has the same amount of noise and same the probability distribution of noise. Therefore, the polar code actually will give you better signal to noise ratio. All right, and then later on, when we move on to digital modulation, you see that the polar code will also give you better energy per bit over the noise energy as well. That will give you better EB over N naught. All right, we're going to use EB over N naught in our practical later on. So that's why I actually introduced the concept of EV over N naught over here. Okay, and what does that mean then? Better SNR, better EB over N naught. What does that mean? That means at the receiver, yeah, your signal power is going to be very much larger than your noise power. And therefore, is make your detection of your signal much easier, isn't it? All right. And then that means your receiver is less likely going to make mistake in decoding the original data. All right. So that actually means that it's going to have lower error or less error. Okay, less error at receiver. Okay, you may need some time to copy this down. So let me know when you're finished. Tell your friend I can't admit him. If I admit him, I need to stop here and stop here. Everything I wrote here is gone.
This time.
So let's move on to the next slide. Okay, this slide basically show how we can multiplex the line codes from different sources. Okay, a lot of times, all right, a lot of times the capacity of a channel, right? In this case, your cable, right, of transmitting data is always larger than the data rate of the individual sources. Okay, so what it means is the channel actually can transmit data at a much higher rate, all right, than the rate where data is being created at the source. Okay, if and with this, to actually maximize the capacity of the channel, right, we can actually combine several sources, all right, again through a digital multiplexer. All right, so it's the same concept in the TDM of the PAM that I talked about in the previous chapter. Right, it's the same. So again, if you look at the diagram on the left hand side, here we have a digit interleaving. All right, in digit interleaving, what it means is, okay, now we have four sources of data: source A, source B, source C, and source D. All right. So these are the bit streams from source A, bit stream from source B, bit stream for source C, and bit stream from source D. Now we want to combine. All right, we want to combine this bit stream from these four sources into one, so that we transmit them over the channel. Okay. So again, we use time division multiplexing. Yeah, because it's over time. These bit stream are generated over time. So what we do here is we take the first bit from source A first, and then we transmit. Yeah. Then we switch to source B, and we transmit the first bit from source B. Then we switch to source C and transmit the first bit from source C. Right. This is followed by switching to source D and transmit the first bit from source D. Right? Then we switch back to A to transmit the second bit from source A, followed by transmitting the second bit from source B, then followed by the second bit from source C, and then the next one is second bit from source D, and then we switch back to source A and transmit the third bit. All right, so this is what we call digit interleaving, or you may want to call it bit interleaving. We actually transmit bit by bit. Okay. And we can also do word or byte interleaving. Okay, word or byte interleaving. In this example, I'm showing you is a 4-bit word only. All right. So what we do is we transmit all the 4 bits from channel A first, followed by the 4 bits from channel B, followed by 4 bits from channel C, and then followed by 4 bits from channel D, then back to 4 bits from channel A again. All right, and then everything repeat itself. That is for word. And then for byte interleaving, instead of transmit 4 bit from source A, we transmit 8 bit at a time. All right, because byte stands for 8 bit, isn't it? You transmit 8 bit from source A, followed by 8 bit from source B, 8 bit from source C, and then 8 bit from source D, and so on. Yeah, that is for byte interleaving. And then the last one, the last example is to how to perform interleaving. All right, if we have sources from with a different bit rate. Okay, so the digit interleaving and word or byte interleaving works well if all the information sources have the same bit rate. But if the sources of information has different bit rate, then we can actually use the following methods. Yeah, and this is called TDMA, time division multiple access. Yeah, and how it works is this: if you look at the bit rate for these 4 sources, A actually has the highest bit rate. All right, well, B, C, and D has a lower bit rate. Yeah. So therefore, we actually spend more time in transmitting the bit that come from source A. Yeah. So how this is done in this example is we send the first bit from A first, right? Then followed by the first bit from B. Then we switch back to A, transmit the second bit from A. All right. After that, only we transmit the first bit from C. Yeah. Then we switch back to A again to transmit the third bit. Yeah. Then after that, only we transmit the first bit from D. Yeah. After that, we switch back to A. All right. So this is called time division multiple access, and it's used when not all the information sources has the same data rate. Okay. So okay. So before I talk about pulse shaping, let me stop here for a while to admit those who requested to join just now. Um, where are they? Disappear already. Okay, never mind. All right, so let's move on to pulse shaping. Okay, so the line code that we have generated so far are actually rectangular in shape. All right, rectangular in shape. But in practice, if we don't really send the rectangular pulses as they are, for two reasons, the rectangular pulses is going to occupy a very large bandwidth. Yeah. And then second thing is the rectangular pulses. If not dealt with properly, it will overlap. So once it overlap, then your signal won't be able to recover correctly. Yeah. So and then because when we transmit digital information, we do a lot of sampling, right? We'll do a lot of sampling. At the receiver also, we need to do sampling. So one of the sampling meaning you actually read the voltage, okay, the level at the right time. Yeah, at the right time. So therefore, to actually make sure we read the message at the right time and make decision at the right time, we must sample the signal at the right time as well. All right. So how to actually sample the signal at the right time? In order to do that, yeah, so basically we need to sample signal at the same rate where we actually at the receiver we need to sample it at the same rate when at the same rate as the transmitter. Yeah, so we need to synchronize them. That is one. And second thing is the transmitter have to make sure that it transmit pulses that do not overlap at certain time. All right. You have to make sure it do not send signals that are overlapping at a certain times. Yeah. And that is make sure we have zero ISI. ISI stands for what? Inter-symbol interference. All right, inter-symbol interference. You learn about ISI, right, in your digital signal processing? Okay. So to ensure zero ISI, the pulse shape must be a sync pulse. Okay. How a sync pulse look like? A sync pulse basically look like this in the diagram. This one here. All right. So the sync pulse has a non-zero amplitude in the middle when time equal to zero, meaning when you transmit, all right, at time equals to zero, it has a non-zero amplitude. But then the amplitude will be zero at times equals to plus minus n TB. TB is your bit duration. All right. So that means when I send the current pulse, all right, if I send with the same pulse, and next time I send another pulse for the next bit, which is TB, all right, the amplitude of the previous pulse that I send must be 0. All right. And therefore, whatever amplitude that I send at this time TB is the amplitude of my current pulse. Yeah. And sync pulse has this property. Yeah. And then when I send my third pulse, all right, in the next 10 bit duration, I need to send my third pulse. Again, I should have 0 contribution from the previous pulses. All right. So I mean at this time when I send my third pulse, the previous pulse and the pulse that come before that, the amplitude of both of them must be 0 as well. Yeah. Again, so whatever amplitude that I send at this point, all right, is the amplitude that belong to the current bit that I'm sending. Yeah. And therefore, at the receiver, when it actually sample again, when it make want to sample to make decision, it need to sample at this interval also lah. All right. Okay. So that will make sure that the amplitude are detected correctly. Yeah. So no overlap. All right. This will ensure no overlap at the decision making instant or the sampling instant. Yeah. At any other time, pulse overlaps are allowed. Okay. We don't care because we only care about the amplitude when we perform our sampling. All right. So this is the sync pulse in time domain. So sync pulse in time domain, if you will actually plot it, all right, the waveform is going to look like this. Yeah, and 1 over RB basically is your bit duration. Yeah, and if you look at the Fourier transform of this sync pulse, okay, you perform a Fourier transform of the sync pulse, basically you get a rectangular pulse, right? Yeah, and then this rectangular pulse will have a bandwidth of RB over 2. Yeah, and this is the same as the theoretical value, the bandwidth that we have derived previously. Okay, however, this pulse is impractical to generate. All right, it's not easy to generate a sync pulse. Okay, there are many problems related to it, which I won't go into details, but I'll talk about a bit in the next slide. So, a more practical approach is using a raised cosine pulse. All right. A raised cosine pulse basically look very similar to a sync pulse. Yeah. But then if you look at the shape of a raised cosine pulse, basically it's a dotted line here. This dotted line here. You can see that the pulse actually decay much faster as compared to sync pulse. All right. And then the amplitude is the highest here. All right. But at any NTB, you can see the amplitude is 0. 2 TB, the amplitude is 0. And then in between here, meaning by the time the next pulse need to be sent, the amplitude also is very close to 0 already. It actually decay very rapidly over here. Yeah. So that means actually raised cosine pulse is better than sync pulse. Okay. And then if you look at the Fourier transform of this raised cosine pulse comparing to sync pulse, all right, this is what you can see on the right hand side here, the PF. All right, then with the ideal sync pulse, you get a rectangular shape, right? The spectrum is a rectangular in shape. But with a raised cosine pulse, right, depend on the roll off factor. Roll off factor is meaning how quickly you want the pulse to roll to become 0. So if you actually use R equals to 0, R equals 0, meaning this is ideal sync pulse. All right, it straight away roll off. But if you use a roll off factor R equals to 0.5, right, that means it's going to roll off slower. All right, meaning the response is going to go to 0 at a slower rate. Okay, and this will take up 3RB over 4. Yeah, and if you use a raised cosine pulse with a roll off factor R is equal to 1, yeah, then you can see the roll off is even slower. and then the bandwidth is going to be RB. All right. So with raised cosine powers, we compare to sin powers, right? It's not as sensitive to deviation of RB bit rate. All right. So sometimes used to inconsistency or instability in the bit rate. Um, it may give problem when you generate your sin pulses. All right. Whereas if you use raised cosine pulse, all right, it's not sensitive. So the slight variation in your bit rate is still tolerable. Okay, and then sampling as well. Okay, is also insensitive to any small deviation in your sampling rate, and also timing jitter. Timing jitter meaning you actually sample at the right time. Sometimes it can be can have slight jitter in your sampling pulses. All right, then again, raised cosine pulse is not sensitive to all this jitter. All right, and this is important because remember our goal is to ensure we have zero inter-symbol interference. Okay, okay, but and then raised cosine pulse is more practical, it's easier to generate, and it has all these benefits. Of course, we pay a price by having two times the bandwidth lah. Okay, the bandwidth now is RB instead of RB over 2, the theoretical bandwidth for sync pulses. So now our effective bandwidth, so that gives us the effective bandwidth after pulse shaping of 1 plus RB over 2. All right, what is R? R is our roll-off factor of our pulse shaping filter. Yeah. So the pulse shaping filter again will actually, if you use R equals to 1, the pulse shaping filter will produce a pulse. You send in a rectangular pulse, it will actually give you a raised cosine pulse with R equals to 1. Okay, so the response is going to be like this. Okay, and the bandwidth is going to be RP. So again, using this equation, same thing lah. R equals to 1, right? 1 plus 1 is 2, 2 over 2. That give us a bandwidth of RP. All right. So therefore, the bandwidth of the pulse that you send actually depends on your bit rate. Yeah. And then this wave actually can be anything between BT or 2BT, okay, depending on our roll-off factor. If you use a roll-off factor of 0, use ideal sync pulse, then your bandwidth is RB over 2, which is same as our theoretical one. Yeah. But if you use a more practical pulse, which is a raised cosine pulse, so it depends whether your roll-off factor is 0.5 or 0.8 or 1, then your bandwidth will change accordingly. Okay, so that's what it means by here. It depends on the roll-off factor of the pulse shaping filter. Okay. Right. Any questions here? No? Don't then I move on, yeah? So differential PCM. All right. Since I'm running out of time, I want you to read all these things on your own. All right. If necessary, then we go into details. But I think I need to hurry up a bit for your practical session next week. So I'm going to skip all this, and you may want to read it. Okay. I just want to talk about the last two slides or few slides. The application of PCM. All right. And its variants. So PCM, as far as speech signal is concerned, all right, the speech signal, we normally sample our signal at 8 kilohertz. Why 8 kilohertz? Because the voice signal normally is somewhere between 0 to 5, right? So you take an average, let's say our voice signal, the baseband bandwidth is 4 kilohertz, then we sample our voice signal 8 kilohertz, 2 times the highest frequency in the voice signal. And this is normally quantized to 256 levels. That means we use 8 bits. Yeah. This gives us a telephone PCM signal that is going to be 64 kilobits per second. All right, and what it say here is actually the various. Okay, there's a spelling error here. DPCM. DPCM. Okay, DPCM actually stands for differential PCM. Differential PCM, basically the concept is instead of transmitting the exact amplitude of the signal in binary format, I actually just transmit or I perform quantization on the difference between consecutive samples. All right. That means if my current sample is this high, my next sample is this high, I instead of transmitting the entire sample as it is, this high, I just transmit the difference between them, which is this one here. Right? So you can see if I actually transmit the difference between two consecutive samples, right, I actually need a small value only. Right? I only need a small value to actually represent the difference. Right? So with this, we can actually reduce the bit rate. Okay. Why bit rate reduce? Because we need less end. We need less number of bits. Yeah, because the difference is very small. Yeah, so we only need less bits. With less bits, meaning we are going to save on our bit rate. Okay, we can lower our bit rate. Um, and then if you use adaptive PCM basically depend on the differences between two consecutive samples. If the difference is big, then we actually quantize it at a higher level. If we actually the difference is small, then we actually use just a small difference, so we need less bit. Yeah. So again, we can further reduce our bit rate. Yeah. Down to 32. And if you use delta modulation, okay, you read through yourself. Basically, this is a 1 bit DPCM. 1 bit meaning so instead of transmitting the actual difference between the two consecutive bits, I just use 1 bit to represent. Is my current bit bigger or smaller? Is my current amplitude bigger or smaller than the previous one? If bigger, I transmit a 1. If it's smaller, I transmit a 0. All right. So that's basically the concept of delta modulation. So if we use delta modulation, we can even reduce the rate down to 24 kilobits per second. All right. So you can see a direct PCM will give you 64 bit. We can actually reduce it down to 64 kilobits down to 24 kilobits per second. All right, so these are the variants of a PCM that I skipped, but you may want to read through it later on. And then for audio signal, okay, audio signal normally use a 16-bit PCM. All right, 16-bit PCM, that means it's 65536 levels. All right, this is actually one of the tutorial questions. We're going to look at it later on. And this is sample at 44.1 kilohertz. Okay, and then for audio signal, and this is MPEG. There are many types of MPEG, MPEG 2, MPEG 3, MPEG 4, right? Depending on the MPEG standards. Okay, this one is 16-bit PCM, 48 kilohertz. All right, and then if you do compression, then you can compress it down to 64 kilobits per second. All right, so all this just for your info. All right, so you may ask, why we go through all the trouble, convert it analog to digital, and then we need to do sampling, we need to decode, encode, all these things. Okay, definitely we did this for some good reasons. Yeah, and these are the advantages of transmitting our data digitally instead of analog, right? So the first one is the noise immunity. Digital signal actually are more immune to noise as compared to analog signal, right? And then the repeatability is high. Repeatability means we actually put repeater along the transmission path, all right, to detect and then retransmit a new noise-free signal. All right, so basically we put repeater. Repeater is actually just another receiver followed by a transmitter. All right, so it actually kind of boosts the original signal. I wouldn't say boost lah, but receive the signal and then clean it and then transmit again. Okay, uniform representation, digital transmission. Basically, if you look at the signal representation, they are just use ones and zeros, binaries. All right. So it doesn't matter what kind of analog sources we have, all can use the same transmission method, right? So be it speech or audio or video or text, all transmit using the same representation. Yeah. And then the next benefit is on storage and processing, right? So digital signal can be easily stored, isn't it? Yeah, in hard disk. And then processing wise, we always use the digital signal processor. So the same processor can process all kinds of signals, right? As long as they're digital. Okay, flexibility. So digital system are basically flexible because you can just cascade them, all right? And then you can just combine different digital system to actually perform sophisticated function and control, right? Because they are just ones and zero. So it's not like analog where you need to talk about, we need to consider, the input impedance, the output impedance, the frequency response, and all those things. Yeah. For digital system, you don't really have to consider that so much because they're actually built into perform digitally. Popularity. Okay, with more and more digital system being developed, of course, people just it's easier for people to just take and use and integrate them to create a new functional block. Okay, and of course, this come with a price. Yeah, more price to pay is that the bandwidth requirement now is larger. All right, it's a lot larger. And of course, the real world signal is analog. So you need to convert your real world signal from analog into digital. So you need that conversion process. And of course, a digital system is not compatible with analog system. All right. So if you have your system in analog only, so make sure you digitize it before you actually connect it to the digital communication system. And okay, so because in the digital system we need a lot of synchronization, therefore you definitely need a good clock, right? That can provide you a good synchronized signal. Okay, so that I think basically end this chapter. So on next Monday, I'm going to move on to digital modulation. All right, any question before we stop the class here? No question?
No question.
No, miss.
All right, so we stop the class here. I'll see you on Monday then. Okay, bye bye.
Bye, Miss. Thank you, Miss.
Thank you.